Okay, so welcome to the ACIGS webinar series. This is webinar number 33. And today's webinar is on the topic of geosynthetic specification and understanding MARV. And it will be presented by Warren Hornsey. Just to give you a quick introduction about the IGS, the International Geosynthetic Society. It's composed of 44 chapters globally, and within those 44 chapters, there are approximately 4,000 members, and that includes corporate members, individual members, and student members. The ACIGS, the Australasian chapter, we are the chapter that looks after the Australasian area, and that includes Australia, New Zealand, the Pacific Islands, and Papua New Guinea. If you want more information about the IGS, you can visit the website on geosyntheticsociety.org, and on the IGS website there's lots of good resources available. There's information about all the technical committees, there's current news, there's a calendar of events that are happening globally. There's access to the digital library, so this is where you have access to the journals, the geosynthetic journals that are available for all IGS members. That includes Geosynthetics International and Geotextiles and Geomembranes. So all that can be accessed through the IGS website. And following on from that, the ACIGS, our chapter, again, we have our own website with local content specific to the Australasian region. So on our website that you can visit at acigs.org, there's information about how to join the ACIGS if you're not a member. Again, students are free, and there's membership for individual members or corporate members. We are now accepting memberships all year round, but specifically for the 2023 year. It's good to join now, so you get the full year's membership. Again, we've got news, local news specific to the area and what ACIGS are currently doing in the industry. There's a resources section available, there's information for students, and we've also got a webinar library. So all these webinars, they're recorded and they're available through the resources section on our website. So if you've missed one, be sure to check out the resources section, and there's lots of really good content there, and from all 33 webinars, plus some extra content from roadshows and other events. So be sure to check those out. If you would like a certificate of attendance for today's webinar, all you need to do is email info@acigs.org. Let us know that you'd like a certificate of attendance, and we will send one by reply. So moving on to today's webinar, we'd like to thank the sponsor for this event. The sponsor for today's webinar is by Fabtech. We've got Managing Director Graham Fairhead, who will provide a short 5-minute case study after the main webinar today. So thank you for Fabtech for sponsoring today's webinar. It's very much appreciated. And today's webinar, as I previously said at the beginning, is on the topic of geosynthetic specification and understanding MARV. And we have Warren Hornsey with us today, presenting on that very topic. So I'm sure many of you know who Warren is, but a quick introduction to Warren. Warren's a professional engineer. He's got experience in Africa, UK, and Australia. He's the director of TRI Australasia, and he's directly responsible for all geosynthetic testing and supporting the Australasian region. He's got 24 years experience in geosynthetic design, construction, and R&D. He's the past chairman of Standards Australia Committee on Geosynthetics and a past committee member of the IGS. He's published over 20 peer-reviewed papers covering a range of geosynthetic applications and has a passion for all things geosynthetic related. So we will now move on to today's webinar, and I'll pass over to Warren, but just let me make note here that if you have any questions, please post them in the Q&A, and if you could include your name with the question. If we don't get a chance to answer all the questions, we can then ask Warren to answer those after the webinar, and we can then contact you directly with an answer to your question. So I will stop sharing right now and I'll pass over to Warren. Thank you, Warren, for joining us today.
Thanks. Let me just do this. Can you see that all right, Ryan and everybody?
Yeah, that's good. Thank you.
Okay. All right. Well, thanks for coming to see the presentation today. I hope I'm not going to bore you to death with statistics. I know it wasn't my favourite subject at university, so it could be a long presentation or a boring presentation, just depending on how you see these things. So what we're going to cover in the presentation is the definition, what is the MARV. We're going to look at what suppliers publish in terms of data sheets, why I think MARV is important, and then why or how MARV is derived, then how to specify with MARV, and probably most importantly, how to assess whether the product meets specification once you've specified with MARV. The common mistakes I see in terms of analysing results versus MARV specifications, and then what to do when the product doesn't meet specification, how to deal with an issue when there are failures. So in terms of the MARV concept, it was developed back in the early 80s, pretty much by GSR, or the Kerners and the Geosynthetic Research Institute. And it was a middle ground between engineers specifying absolute minimum values and manufacturers providing average values. Initially, it was used only for geotextiles, and that's primarily because we see the largest range in terms of results in terms of geotextiles. They are not as uniform as, say, geogrids or geomembranes. So, but what I've seen lately is it's gone into all geosynthetics are now specified via MARV. So what does MARV stand for? And it's a minimum average roll value, and it's basically for strength characteristics, and statistically, it's saying 97.5% of the results will be greater than that value. And then you have the opposite to MARV, is MaxARV, which is generally used for pore size, equivalent opening sizes, and so on, where statistically 97.5% of the results will be less than that value. So those are the two terms we generally see MARV being used primarily. So we've described what the MARV value is. What you see in terms of suppliers' data sheets that you'll get across your desk or on the web is MARV, typical values, and these are just definitions. So typical is having a distinctive quality of a particular type. So it's very vague in terms of what that number actually is, and in my opinion is designed to confuse people. That's really what it's there for. It's just to muddy the waters when you're trying to pin somebody down to exactly what their material is showing or intending to achieve. Average is good. At least we know what it is. It's in taking adding the several results together, dividing by the number of results you've done, and you get an average value. Then lastly is characteristic, which is unique to Australia, and particularly Queensland, New South Wales road authorities, where they take the average roll value minus 0.83 times the standard deviation of the specimens used to get that average roll value. The actual specification is a minimum, so it needs to be, it's quite simply above that number. It's not a bad way of defining geotextiles because it takes out, or it takes into account the variability of the results across the roll width, and we'll show a little bit more about that later on. In terms of suppliers publish in terms of data. I've pulled up 4 specifications from suppliers in Australia, and you can see the variability in terms of what data is published. On the left-hand side, these 2 suppliers supply typical and MARV values. This supplier over here just supplies numbers and no real definition of what those parameters are. And on the bottom right, we have a spec sheet that shows minimum values next to the values, and yet it says in the fine print down the bottom, typical values. So what you've got to be very careful is that when you're looking at data sheets of materials that people have supplied, that you're comparing apples with apples, or that if you're setting up a specification, you understand what you're pulling from data sheets. Is it a MARV? Is it a typical? Is it an average? Is it a minimum? You really need to look at that very carefully when you're using supplier data sheets to set specifications or to define what material you want in your project. And now, essentially, the manufacturers can publish anything. They can publish minimum values, MARV values, or typical values. And the industry runs on essentially mass. So the heavier the material, the more you're going to pay for it. So it's as simple as that. So if you have a look at these graphs, this hypothetical distribution of results, typically because the material varies, you're going to have some numbers that are low, the majority of the numbers in the middle zone, and then some numbers that are a lower number that's high values. And for a given calculation for the same material, so it's a typical geotextile is 270 grams. If you spec a typical of 270 grams, that's your average weight will be 270 grams. You're going to get some down in the 218 type grams range. If you specify 270 MARV, it effectively increases the mass of the material, and you're going to get some values that while you specify 270 MARV, there's this portion here on the graph, 2.5%, that is going to be less than the 270. But as you move towards the right-hand side of this graph, you are going to pay more for this material. So just be aware of that. And if you specify a minimum of 270, your mean mass is going to jump from 270 grams to 320 grams. So that's just a schematic of what happens when you specify these different values. And why is MARV important? In the past, and pretty much the same time as MARV was developed, Queensland Main Roads did an analysis on what suppliers published in terms of their data sheets versus what they were seeing in terms of test results. And back in 1981, they were showing that there was up to 30% or the values were up to 30% of what was published in their published data sheets. So hence they introduced the characteristic specification, which is now a minimum value. In 2010, Parsons Brinckerhoff did a report which analyzed 5 suppliers' materials compared to their data sheets, and you can see the huge variability in results. In that one supplier had 94% of their results below their published data, and with a maximum variation of 76% below their published value, which is kind of scary. And hence the drive to go for something where moving away from the typical data sheets to something where we expect people to publish MARV values. So in the 80s, similar time to when the Department of Roads in Queensland did their analysis, the USA went into this, discussed how to best present data sheets on information on data sheets. And it and they decided on the MARV calculation, which they simplified to be the average results minus 2 standard deviations. And I'll show you that that's not 100% correct, but it was the best way to simplify the statistical calculation. But what's important to know is that MARV can only be reliably reported if you have a lot of data, if you have a lot of information to work with. If you work off a MARV or calculation which has limited numbers, you can't use the 2 standard deviation calculation. And I'll show that in another slide. But the big thing is in terms of how many roles should be tested in terms of getting MARV values. And D4354 gives guidelines in terms of how many tests should be carried out per the number of roles that you manufacture. And you can see that really, the testing at low roll numbers, if you've done up to 30 rolls, manufactured up to 30 rolls, you need 3 tests. That's 1 test every 10 rolls, give or take. But when you start talking about manufacturing 1,000 rolls, we're talking about 10 rolls. That's 1 test every 100 rolls manufactured. So you need to understand that the results that you're getting calculated in terms of MARVs are still taken on relatively low numbers of tests compared to the actual rolls that are produced. It's also important to know that the manufacturing becomes more efficient in long runs. As a manufacturer, you don't want to be swapping between grades. You can fine-tune your product if you have the time to run it for a long time, and you can make small changes and improve it and get better results. But to give an example here, that if you manufactured, say, 500 rolls, you'd have a total quantity of 450,000 square meters. You're required to test 8 rolls, which means that every 56,250 square meters, you're going to get a test. Or 90,000 if you're testing 1,000 rolls. Now, most of the projects that we deal with are less than the 56,000 square meters. So some of the product that you get on site may not have been tested by the manufacturer at the end of the day. It's also important to note that geotextiles, while we think they're relatively geosynthetics are relatively consistent, and for geogrids and geomembranes, that is reasonably true. In terms of GCLs and geotextiles and geocomposites, that most certainly is not the case. And this example that I'm showing you here is essentially peel strength across the roll of a GCL. Essentially, the test requires 5 specimens to be taken across the roll width. And what we did was we tested 15 specimens across the roll width. So we tripled the amount of testing. And what you can see in each of these circles is a section of roll, 300 millimeters long, that we've taken 3 specimens are. And you can see the variance in the strengths across those 3 things. So that's 1 specimen, essentially, that you've got that variability in the result. The second section, the next 300 millimeters on that same roll, the variability is quite high. The next 300 millimeters, again on the same roll, it's the same roll that was tested, you can see the values that are changing. And you can see across the roll width how the peel strength varies through there. And if you were unlucky and you selected this point here, this point here, this point here, and up here and down there as your peel strengths, you could get a very different result from when you're picking up the peaks. So it's important to know that these materials are not that consistent, and that the MARV should take into account these values along the way. So essentially, this is the ideal situation where most of your results are within this band of 2 standard deviations, but there's always going to be an outlier section, this 2.5%, either above or below, that you're going to get results in. And that's not values that the manufacturer necessarily has tested, but it's roles, because we're testing 1 in every 10 or 1 in every 100 roles, we're not going to test every role. So there's going to be some data missing from your data set. And that's what that falls into that zone there. And this graph essentially shows the type of variability that you can see in a production run over time. So this is roles tested. This is not roles manufactured. This is roles tested. And you can see the big variability in results during the manufacture of these materials. So don't think that the stuff, because it's man-made, is exactly the same over and over and over again. There's things like needle wear that come into place, polymer quality, and GCLs, the interaction of the clay with the needles, and so on. So be aware that while everything's done to make a very uniform product, that there will be variability in this material during manufacture, and the material that you sent out to site will be variable. Now, the true calculation of 97.5% confidence level should be calculated on or derived based on the number of tests that you do on the material to get that result. And to use what our common acceptance of MARV is the mean minus 2 standard deviations. You effectively have to have done 60 tests on that material to get to use that value of 2. The issue is that many manufacturers won't have that number of tests on a given product, because every time you change your polymer or you change your type of needles that you use, that data, then you have to start your data set again. So from a manufacturing perspective, to purely to work off of 2 is dangerous from their perspective, because the lower the number of results is, you should be applying a higher factor to obtain your MARV value. So that's important for you to know how the manufacturers get there. But as a designer, this is not important stuff, because all you want to do is compare the number against your specification, or the test results against your specification. So in terms of the calculation, you get these individual roles that have individual specimens. The individual specimens are averaged to get an average roll value. All those average roll values you get an average on the average roll values, and you get the standard deviation on the average roll values, and then you calculate your MARV out of that. So that's effectively how the system's done. And this number here, while we specify, it states 2, a responsible manufacturer will apply some factor of safety or some factor to that to allow for either numbers being different or inter-laboratory variability within laboratory testing, or where the materials are sampled across the roll. In terms of specification, what you want to make sure that you're doing as a designer is to make very clear what you require. If you require MARV, do not include the word typical or average or minimum amongst that. Don't mix the terminologies, because that just creates confusion. So the only area that potentially typical values or average values are used is in pore size and flow rate. And that's where I often see problems coming in, is people will specify MARV or max ARV and then take the average or typical values off the data sheets. So just be very sure when you're taking information off data sheets to put into your specs, that is actually what's out there, because we often get problems running it, but typical is expected, and we compare that to a max MARV value. So just make sure that you understand what you're putting together. And the other area that we often see problems in is that where people increase the strength of the product, and that often leads to a reduction in, well, it will in most cases lead to a reduction in pore size and flow rate. So when you specify things, don't mix and match. Don't pull the strengths from one thing and say, well, I like the strength of that grade, but I really like the pore size of that grade. It just doesn't work like that. There is a relationship between mass and pore size and flow rate, and you can't mess with that. So the area that we often get called into is dealing with what is a passing and what is a failing result when you specify with MARV. So essentially, most laboratories should give you a report that shows the individual specimen values. And in the case of CBR strength, we test 10 specimens and we get the average value, the average roll value. Now that is the number that needs to be compared with the specification of in this case, 3,400 newtons. Even though that there are lower numbers in there, so we're looking at a 3,235 newtons there and 3,159 over there, that doesn't matter, because what we are comparing is the average roll value, and the average roll value needs to be above the specified minimum average roll value. So that's what you need to compare with. That's the first thing to take into account. So those numbers that are low within the specimen range, that's not important. So let's look at, this is an actual case. So I've taken this data, this is from a project, these numbers are real numbers, they're taken from a project, and we can go through, and I'll use this template or this set of data to explain a number of things that we're going to go through in terms of looking at this data. So the first roll, look, the first thing was, yes, that initial roll passed the specification. But essentially here, 4 rolls fail because we have rolls, these rolls over here, that are all below, the average values are all below the minimum average roll value of 3,400. So you get 4 rolls passing and 4 rolls failing out of this batch. And that's all you need to know at this stage, is that the rolls are failing. So we spoke briefly about it. The common mistakes that I see is people comparing the specimen values against the MARV value. That's incorrect. You need to do the average roll value. I also see people taking the standard deviation of the specimens. So we'll take the mean of the specimens, get the standard deviation of those specimens, and saying the mean minus 2 times the standard deviation. That's not correct. That is not the way you calculate MARV. Again, it should just be compared to that average roll value. This is something similar to the characteristic value that the Queensland and New South Wales Forest Department uses. And then the next one we look at is applying the calculation to a number of rolls. So maybe you get 4 rolls that are supplied to you. And in this case, all 4 rolls pass the MARV value. They're all above the 3,400 value. But then people apply a statistical analysis. So they take the mean of those 4 rolls and then minus 2 standard deviations. And they say, well, it's failed because the MARV fails. But that's not the correct way to do it, because you're taking just a small snapshot of results. And that's not how it should be done. So the reality is that if you specify geosynthetics, sooner or later you will get a failure, because essentially what we've seen from the amount that manufacturers are required to test their material, that the vast majority of materials that are going out are not tested. And while they do everything in their power to ensure that it's meeting specification, there will still be, because of this MARV calculation, 2.5% of the material supplied to site that will fall below specification. So therefore, you must set up a procedure of how to deal with the situation when it occurs. What you don't want to be doing is specifying MARV and then not have any process in place to deal with the issue when you have a failure. That's the worst situation to be in. So what I've looked at in the rest of this presentation is two options in terms of how to deal with this issue when you have failures occurring. There's the GRI White Paper 10 that deals with it. It's a good document to get access to. If anybody wants a copy of that, just let me know and I'll get you that. And then New South Wales EPA has included in their documentation or their specification on how to deal with failures should they occur. And I'll go through both of those scenarios here. So in terms of the GRI white paper, their examples is 200 rolls supplied. Of that, 6 rolls were tested as per the ASTM requirement. And 1 roll failed to meet specification. What is the next step? So GRI then says you retest 6 new rolls. If all rolls pass, you accept all the rolls. However, if one of those new rolls fails, you reject all 200 rolls, which is a pretty punitive thing to occur. But that's the way GRI has set up the acceptance criteria. So you can choose to go with the GRI methodology or alternatively a different methodology. Now, if we look at the example that I showed previously where 50 rolls were supplied to site, 8 of those rolls were tested, 4 rolls failed to meet specification. Immediately, all 50 rolls would be rejected because you've got more than 1 roll failing in your test program. So there's no comebacks, it's just reject all 50 rolls. So if we then look at the New South Wales EPA method, and we look at those same 50 rolls supplied, 4 rolls failed to meet specification. New South Wales allows retesting of the failed rolls, but it not just the parameter that fails. So you may, in this case, CBR failed. You need to retest all the parameters. So the full set of parameters, RAG, trap tear, all the rest of it. If all the values pass on those 4 rolls, you accept all the rolls. If any of the parameters fail, you reject all failing rolls that are between the passing. So you isolate the failing rolls. So you basically bookend the rolls that are failing, and I'll show you in terms of this example. So we had 8 rolls tested. These 4 failed. We ran retests on them. 2 of them passed on retest. So therefore those rolls are acceptable. But essentially from roll 22 through to 41, those rolls had to be replaced. So instead of replacing 50 rolls now, we're replacing 19 rolls. So while it is still not something that the supplier would necessarily like to see, at least it minimizes their exposure in this thing. And I think it's a reasonable way to go with this methodology. So, in conclusion, what you need to understand is geosynthetics aren't as uniform as you'd like to believe. The calculation of MARV is up to the manufacturers. That's what they have to live and die by. That's how their products is going to be assessed. The engineers that are specifying, all they need to know is whether the test results that are coming back meet that value or not. And that's all they need to worry about. what the engineers have to be very careful with is comparing data sheets with the specifications in terms of what are you looking at, particularly when you're approving something that somebody puts forward a typical value and your spec says MARV, you need to be assured of that. And then in your specification, make sure you clearly define minimum MARV, max ARV, or whatever you choose to do. Make sure there's no ambiguity in terms of what you want out of your specification, and that your specification also deals with how to overcome the issue or how to deal with failing rolls at the end of the day. So if that's all you can get out of this thing is the 2 lines on the last thing, make sure that your specifications define the right characteristics and that you know how to deal with failure when it occurs. Because from my experience, if you specify with geosynthetics, sooner or later you're going to get a failure, and you need to be able to deal with it. And if the specification is clear, a lot of the troubles that we see in terms of the interactions between contractors and suppliers and consultants are dealt with within the specification. It's when it's not dealt properly within the specification that a lot of the big arguments come along, and yeah, lots of money gets spent or lost along the way. So that's the end of my presentation. I'm happy to hand on to Graham now.
Yeah, thanks, Warren. We've had a few questions that have been raised, but we'll get to those after we've had today's sponsor, Fabtech, presented by Graham Fairhead. Yeah, we'll have Graham's case study and then we'll move on to questions at the end. So yeah, thank you. Over to you, Graham.
He's on mute.
Ryan, I think you need to turn my camera on.
Well, we can see your slide presentation.
Yeah, no, Ryan turned me off earlier. Thanks, Warren. Warren opened with a quote that's actually from Benjamin Disraeli. Just like to point out that he made it for 6 years as Prime Minister in the UK, somewhat better than Liz Truss. And there's another quote there, interestingly from a similar timescale, early 1900s, from Alan McKay, which I think is particularly poignant. We shouldn't be using this data to incorrectly categorize material. It should be used to reveal good material and reject bad material. Now, I was asked to provide a couple of practical examples of MARV being used in industry. So the first one here is just using the HDP specification, GRI GM13. You can see in the highlighted area, if I can work out how to do that. In the highlighted yellow, nearly all of the measurements are described as min-av. And that applies to all of those tests. And in the case of thickness tests, there's 10 tests per roll. If you look at UV, for example, there'll be a single test. So while it says min-ab, it's an overall blanket statement to say whatever number of tests that you take, you average those tests, and it's the average of those tests that you compare with the specification, and it has to exceed the spec or be below the spec, whichever it might be. Min-ab is not the same as MARV. Second example here is nearly all specifications. There's 3 different specifications here. Nearly all specifications we see now wouldn't have been the case 5 or more years ago, but now they all have in some way MARV quoted in the specifications. And in the case of HDPE, the Geosynthetics Institute, in their paper, white paper number 10, specifically recommend not to use MARV with geomembranes. They argue that geomembranes are quite stable products, unlike the fabrics, and you shouldn't be using these statistical processes. You should be using the absolute minimum approach, as Warren explained at the very beginning. And yet we see MARV appearing in these specifications. and its application is not entirely clear. If you look at the bottom example here, where they've specified MARV, and then they put a footnote specifically saying the definition that we know, it's this 95% confidence that results are better than, but it's not clear whether that's saying that they're going to allow 2.5% failure rate, or whether they're just referring to the fact that MARV statistics should be applied by the manufacturer. It's left to interpretation. And then this third example highlights the commercial consequences of this issue. So this is a project from last year, a supply of 2 millimeter HTPG membrane. It was in Victoria, so this is a pretty mature marketplace in terms of some relatively strict specifications. It should be understood. At the bottom of the slide, you can see note 11. It very specifically says the compliance of these properties shall be calculated based on MARV values. Well, I think that's probably okay to understand. But does that mean that you apply that data, that term, to the measured results or in the manufacturing process? That's far less clear. And they've applied that note to quite a few properties, including OIT and oven aging and so forth, where there wouldn't be sufficient test samples to do that. What actually happened, the materials were supplied, as is the case in Victoria. They were sampled on site, independently, sent to an independent laboratory to be tested, and nearly half of the materials failed thickness, 90% failed tear, 70% failed yield, which meant that there wasn't a single roll that actually passed everything, and the entire supply was rejected. And that was because for each of those tests, the designer's CQA person did that statistical calculation, standard deviation, worked out what the range would be, and said, look, from the full range, you should be getting failing samples. And that's how they applied the data on a roll-by-roll basis. And there was no consideration for the commercial consequences of that approach. There was no support for the CQA engineer to help him interpret the data. Having rejected an entire supply, there was no check process to say that's quite severe. We better make sure we're happy with the outcome here. And the entire supply was rejected without any red flag review. In terms of commercial consequences, in this particular case, the order quantity was around about $500,000 of material, so not a trivial number. And the material had to be resupplied with project delays. Now, actually, what did happen, there was quite an extensive review of the correct application of MARV, and ultimately the material was accepted because it did all comply with the normal application of a GM13. Quite a time-consuming and stressful process for most people involved, including the client, who was exceedingly concerned that they were going to face some significant penalties because they couldn't build their landfill. So there's three quick examples. From a practical point of view, the application of MARV, pretty much, if it's done correctly and the manufacturer has done what he's supposed to do in terms of defining the characteristic of his material, and has got a bit of a safety margin to the min spec, it's really about everything should pass. If it doesn't pass, it should be rejected. And that acceptance criteria is either min av, or Warren was using the expression average roll value. It is the average of the multiple tests that are done on a single sample. And MARV is effectively a manufacturer specification. It's not an issue for day-to-day material acceptance. Warren said as well, unambiguous specifications, especially if a designer does want to deviate from the norm for some good reasons, make it really clear how you plan to deviate, and that it's not dare I say, careless drafting of a specification. It's very deliberate. Important to have qualified, experienced staff reviewing this data. There is actually an ASICS paper on this topic. The reference is there on the screen, which is very helpful. And Kerner's white paper number 10 is also useful. That's my quick input, Ryan.
Thank you, Graham. Thank you very much. Yeah, some useful information there, and we've got a few questions that have come from this. And again, I think the questions actually show the uncertainty on MARV and what it is. I've got a question here. So I'll leave it open to both of you to answer, but I have the understanding that the typical value is 10% lower than the MARV value. Is that right? I mean, there we go. That's not,
values 10% lower than MARV. No, absolutely not. I mean, typical values are going to be higher than the MARV values. That's no. The typical values are the average values.
yeah.
The MARV values are.
So 50% of the values would meet that, and 50% would be less than that.
Yeah.
And it varies enormously, Ryan, product by product. You can't. Right. There's not a standard answer to that question for GCLs versus geomembranes or grids.
Yeah, I mean, I could give an example based on testing of GCL peel, for example, because of the way GCLs are manufactured. You have obviously for a needle punched geosynthetic clay liner, you have the needle punching process. The needles are changed on a frequency decided by the manufacturer. They may observe a property change, or they may use a specific time that the needles are used for. And because the peels can range from whatever the manufacturer deems as a minimum all the way up to a fresh needle that would give you a really good peel value, you can have that much variability in a peel number that if you applied a MARV calculation to that, you can end up with a negative number. So there's certain properties that you just can't apply this MARV calculation to. So another question here: when is the manufacturer recommended to update its data sheet? Every month, every machine maintenance?
Look, I know in the US they talk about it as the annual process. And most manufacturers will update their data on a monthly basis, and they will keep checking their data and make sure that their numbers are coming out within what their specifications are. So manufacturers will set a manufacturing minimum that they know will ensure that they achieve their MARV values that they do. It's not straightforward, and it will vary from product to product, but they will set a manufacturing minimum that makes sure that their MARVs are met. They wouldn't be changing their specs very regularly. They've set their specs and changed their manufacturing minimums to suit their specifications rather than changing their specifications on a regular basis. But they need to be constantly monitoring their manufacturing results to make sure it's meeting the MARVs. That's essentially it.
Okay, thank you. And another question here. So for the main types of geosynthetics used in landfill construction, could you suggest the best specification parameter to use? So for example, for a geotextile, would it be a MARV? For a geomembrane, would it be a minimum or an average? For a GCL, would it be MARV? Do you have a specific guide there?
Look, I think MARVs, and this is my personal opinion, I think MARV is the right way to go for it. I can understand geomembranes maybe saying minimum, but I understand the logic behind the MARV concept. The reality is that using the MARV allows you, in my opinion, allows you to do retests on the material and check either that it's not a mistake by the laboratory or variability in the laboratory between laboratories. If you just say minimum, it immediately fails. There's no comeback, is the way I see it. So I like the concept of using MARV because it allows a bit of flexibility. It allows you to retest and reassess the material. Minimum is, in my opinion, a little bit too tighter, the specification, but that's my opinion.
Well, I'd add something to that. The geomembranes are usually referenced by thickness, and the way the reference standards have evolved, if you with the resins currently used, if you achieve that thickness for most of the properties, they're easy to achieve. You never get a failure on mechanical properties, for example. There's 20%, 30% more a gap between the low values and the specification. So that's partly why it's not an issue using minimums. It only becomes an issue minimums with membranes on the durability testing, on OIT results and so forth.
Yeah.
And that is then troubling, as we all know, that can be with the repeatability and reproducibility of some of those results. That can be a bit challenging, but I'd still endorse MINS for geomembranes. There's also an issue about how much of this is the manufacturer's responsibility to ensure their product has sufficient gap between their low roll values and the specification, and they should make sure their manufacturing process keeps a gap there.
One thing I would say is either minimum or MARV, not typical, not average, minimum or MARV. Those are the options that you have. And I agree with Graham. The way, particularly the GRI specs are with geomembranes, if you've got your thickness right, it's virtually impossible to fail the other characteristics that are out there. But geotextiles, GCLs, and so on, no. Geocomposites, there's a lot more variability.
All right, I've got a couple more questions here. We've got about 8 minutes left. In the typical average value calculation, are the rows failing the MARV test also included? In other words, how exactly is the typical value obtained? For the example, 3,400 kilonewtons in the 3,400 newtons in the example. Thank you.
Well, okay. So in most cases, those numbers, the numbers that are put in specifications, are taken off people's data sheets. Engineers tend to use published data sheets to define their parameters, because they're not going to come up and invent a new product necessarily unless there's something truly unique about the material. So therefore, they rely on the manufacturer's data for that. And there is an ASTM method for the manufacturers in terms of specifying how they define their MARV values in their data sheets. And that says you should include failing rolls in that calculation of MARV. So yes, it needs to be included in the calculation of MARV.
Thank you. And we've got one more question here. So am I correct that a roll is taken as failing if one of the test parameters does not meet the specified MARV value? If the only test parameter that fails is mass per unit area, should that roll be deemed to have failed?
Okay. My take on it as an engineer, you should only put, if you're specifying something, you should only put in values or numbers that are critical to your design. So if you don't believe mass is critical to your design, that shouldn't be in your specification. If it's in the specification and it's critical to your design, yes, then to reject it. But that is the challenge for the engineers. Don't put in numbers that are not important to be tested, because A, you're wasting your client's money because you're paying to get that done. And B, if there's a failure, you have to explain why that's not important. And that's the reality in somewhere like Victoria with the BEPM system with auditors. If you have a non-conformance, even if it's mass, and you may not think that's important, you are going to have to justify why you no longer require that parameter that you've set in your specification. So it's as important deciding what you're going to put in your specification as to how you define it.
All right, thank you very much. And I think that brings us to the end Oh, we've got one question here. How does MARV differ from the characteristic value used by ISO?
Well, that's definitely you, Warren.
I'm not sure about that. As far as I understood the characteristic value, let me go back and find out a bit more about it. But as far as I knew that the ISO method went, I thought it was 95% confidence level, but I might be wrong. Just let me. We very rarely see ISO over here, so I can't really talk on the ISO side of things. But I seem to remember somewhere 95. Ryan, you would know better than me.
I can't remember either. We'll find out and we'll email you the answer. Okay, so that brings us to the end of today's webinar. Thank you, everybody, for attending. Thank you, Warren. Thank you, Graham. That's the last ACIGS scheduled webinar for 2022. We will soon have the schedule for 2023 established, so keep an eye on the ACIGS bulletins for and the website for 2023 webinars. We have a ACIGS AGM annual general meeting that's being held next week on the 10th of November. So anybody that wishes to attend that, you can access the meeting via Zoom. So if you get the ACIGS weekly bulletins, you'll have a link in the bulletins for that. You will find out who the next committee members are for the 2023 and 2024 period will be. So yeah, be sure to join us, and thank you very much, and goodbye. Cheers, guys.
See you guys.
Thanks, Graham. Bye.
See you, Ryan.